Hello and welcome to another mathematics video in which we seek to analyse and solve ordinary differential equations. Well, in equation 1 here we have yet another non-linear ordinary differential equation, and it's non-linear because of this squared term here. In particular, we have dy by dx and y squared terms. If that had just been x on its own and that had been squared, then it wouldn't have been a non-linear equation, it would have been linear. It's only non-linear because of the existence of the dy by dx and y squared terms. So, as before, the logical thing to do here is to start by trying a substitution, or finding out if there's some way we can use a substitution that will result in the non-linear equation in one being able to be written as a linear ordinary differential equation. Well, the best way to start with this one is to let I'm going to say let v be equal to x dy by dx minus y, right? So if we differentiate the left hand side, we get dv by dx, and that's equal to, well, we have to differentiate the right hand side via the product rule, so we leave the x alone and differentiate the dy by dx, so we get x d squared y by dx squared, and then we differentiate the x and leave the dy by dx alone to give plus 1, which I won't write down the 1, but it's dy by dx. And then, of course, we differentiate the minus y term and we get a minus dy by dx. And as you can see, this dy by dx cancels with this negative version. So what we're left with is dv by dx is equal to x times d squared y by dx squared. So from this, we can deduce d squared y by dx squared is equal to 1 over x dv by dx, right? So substitute, I'll give these equations some label names. We'll call that equation 2, and we'll call this equation 3, right? So substituting equations 2 and 3 into equation 1, we get ax cubed times, well, we're substituting this term in for d squared y by dx squared, so we get a 1 over x times dv by dx. Let me just make that d look a little more like a d. I'm writing right on the edge of my my electronic pad. So that is the left hand side, and that's equal to, on the right hand side, v squared. So, well, we'll call that equation 4, right? So before we go on to the next page, you can see that one of these x's cancels with the x here in the denominator. So if we go on to the next page, we can simplify that expression and write ax squared, but we'll have to put therefore ax squared dv by dx is equal to v squared, right? So we'll call that equation, let me see, what did I call the previous one? It's almost the same equation, but we'll call this equation 5. Now, you can see that equation 5 is separable. So we can rewrite this as dv over v squared is equal to dx over ax squared. And that's supposed to be a d, which I know doesn't look like a d, so we'll just rewrite it. Right, d, there we are. And of course we have to put our integral signs in. We'll call this equation 6. So equation 6 is very easy to solve. Well, hopefully, for people doing ordinary differential equations at this level, it should be. So 1 over v squared dv integrates to give minus 1 over v, and that's equal to 1 over ax. Actually, it's minus 1 over ax, because 1 over x squared integrated is minus 1 over x, and of course we've got the a there, and we have a constant of integration which we'll call c. Now I won't give that a label right at this stage. I'll just say that we multiply through by minus 1 to get, and I'll write it here, 1 over v equals 1 over ax minus c. And we can rewrite that to give 1 over v equals 1 minus acx over ax, right? So that is equation 7. Now I'm just going to amend this equation 7 slightly by replacing the minus ac with a plus b, the constant plus b. It doesn't really matter, it's only a detail. It doesn't really make any difference. You can keep the minus ac in if you want, but it's a bit easier and tidier if we replace this ac with the capital constant b. So what we'll do is we'll go on to the next page. So we've got, and I'll write this in green. So we've got 1 over v equals 1 minus 1 plus, well, yeah, 1 plus bx over ax, right? So let's just see. So we've replaced, I can find my pointer. We've replaced this with the constant b to get this. And if I just go back to black, so what we can do now is invert both sides of this equation. So therefore, v is equal to ax over 1 plus bx, right? So what we've done there is multiply both sides by v, multiply both sides by ax, and divide both sides by 1 plus bx to get this. So what equation number shall we give that? I think we'll call that equation 8. Yeah. So what we now, we can't do much else with equation 8 unless we resubstitute for v. So we need to resubstitute for v. But what is v? well, let's just go back and have a look at what we defined v to be. Well, we defined, if I can find my pointer, we defined v to be x dy by dx minus y. Basically, we substituted v in for x dy by dx minus y. So now we're going to take the right hand side of equation 2 and resubstitute it for v. Okay, so if I just change back to green, since v is equal to x dy by dx minus y, then we have, better go back to black I suppose, we have x dy by dx minus y equal to 1 plus, whoops, making a bit of a mistake there, is equal to ax over 1 plus bx. Now we'll call that equation 9. Right, so how do we solve this? Well, what we've actually got here is a linear ordinary differential equation. We've linearized it. So we've got something that's ultimately easier to solve. Well, hopefully anyway. So what do we do? Well, we want to get rid of the coefficient in front of dy by dx. It's usually what we do in these cases. So we divide both sides by x. Let's make that look more like a division sign. So we divide by x to get we'll I think we'll stick with black on this. So we get dy by dx minus 1 over x times y, and that's equal to a over 1 plus bx, right? Now, the x there has disappeared because we've divided we've divided throughout by x, basically. So if we cut and paste that, because as you can see, I haven't yet cancelled out the x on the right hand side, but this equation simply becomes, as I said before, dy by dx minus 1 over x y equal to a over 1 plus bx. So I just did that on the previous page, and then I added in the x's here and here to show you what I'd done. So I hope that wasn't too confusing. We'll call that equation 10. Now, to solve equation 10, we need to use an integrating factor. So we use an integrating factor, e to the power of minus the integral of 1 over x dx. And that's reason why we choose minus 1 over x as the inside the integral sign is because of this term here, minus 1 over x. So that becomes e to the minus log of x, which is equal to e to the log of x to the power minus 1, which is just equal to x to the minus 1. And or if you could write that as 1 over x, right? So we now multiply through both sides of equation 10 by x. So, well, I'll write in red, 1 over x times dy by dx minus 1 over x y, which is equal to 1 over x times a over 1 plus bx, right? Oh, we'll call that equation 11. Ooh, call that equation 11. There we are. Now we can simplify this to give 1 over x dy by dx. Let's write that a little bit. Let's write that more neatly. 1 over x dy by dx minus 1 over x squared y. See, we're multiplying everything out by the 1 over x. And likewise here, we've got a all divided by x times 1 plus bx. And we'll call that equation 12. Right, now then, I'm going to cut and paste that last equation. And in fact, we'll include the equation label as well. There we are, add to new page. So by now you should be familiar with how to write the left-hand side. So the left-hand side can simply be written as d by dx bracket of 1 over x. So always this coefficient here after you've multiplied through by the integrating factor, which is what this is, 1 over x. So we write down the 1 over x, and then we don't want this term. That's the function of x that we've already multiplied the integrating factor by. What we want is to write down this y term. So we put a y there, and that's equal to a divided by x1 plus bx. And we'll call that equation 13. Right, now okay, before we do the next step, first of all, we'll write this in integral form. So we have 1 over x, y. So if we integrate both sides of equation 13, we get 1 over x times y equals, I'll put the constant a outside the integral sign, and we have a dx because we're bringing a dx up here, and that's over x times 1 plus bx. And we call that equation 14. Now we need to expand, I'll write this down, expand the right hand side using partial fractions. I'll just write PF. That doesn't look like a brilliant P, does it? Right, okay, using partial fractions. Okay, so let's cut and paste this and move on to the next page. Right, so move on to the next page. I'll do this, let me see, oh yeah, just a minute, we'll mark a little space for rough work. So let's just draw this line down here. Now, let's change to green, a green nib. So we want to express 1 over x times 1 plus bx in the form a over x plus some constant c divided by 1 plus bx. Now that c is different from this b. That's why I've called that c, not b, because we don't want to get them confused. So if we multiply both sides by x times 1 plus bx, we get 1 equal to a times 1 plus bx plus cx. So we've multiplied through by all of this in the denominator on both sides of this equation. So when x equals 0, you can see that this is equal to 0 and this is equal to 0. So we're left with, I'll just get rid of what I wrote up there. There we are. When x equals 0, 1 equals a, it's actually a times 1 plus 0, but you just leave it as a. And we can write that as a equals 1 if you like, if you're that fussy. Okay, so now we've found our first constant a, what is our constant c? Well, let's just draw the red line down there. Now when x is equal, well, we want to make we want to get rid of this, make this 0. So the best way to make that 0 is to let x be equal to minus 1 over b. Minus 1 over b. So I'll just write this down here. We've got 1 equals a times 1 plus b over minus b. So that becomes a minus. So we've got 1 equals a, 1 minus 1, 1 equals 0, which you can't have. But also over here we've got plus c times minus 1 over b. And then here we've got minus c over b. Therefore, c equals minus b. Right? Okay, so it's very rough working. So this means that if I just get rid of all of that, maybe I should write it down a little bit more, a little more convincingly. So basically, when x is equal to minus 1 over b, we've got 1 equals c times minus 1 over b. So b equals minus c, or likewise c equals minus b, right? So now we can write the right hand side out in terms of partial fractions. So we've got a times the integral of 1 over x dx plus, well, actually it's going to be a minus sign, isn't it? So it's going to be minus a times the integral of b over 1 plus bx. Right. So 1 over x y on the left hand side is equal to a log of x on the right minus a b log 1 plus bx, but we have to differentiate what's inside the bracket. So that becomes b. When you differentiate 1 plus bx, it becomes b. And so we divide by b. So now we have 1 over x y equals a log x minus a log 1 plus bx. Oh, and actually, I forgot to write in a constant. So it should be a constant of integration. I'll write it down here. Plus, what shall I choose? We'll call it d. I think that's what I've got in my notes. So 1 over x times y equals a log x minus a log 1 plus bx plus d. Right, so let's go to the next page. I'll just write that out again. 1 over xy equals a log x yeah, minus a log, whoops, 1 plus bx. I've actually put modulus signs in there, plus d, because before I just had brackets, but it doesn't really matter. So y is therefore equal to, well, first of all, before we write what y is equal to, let's just leave that as 1 over x times y. Now, we can take out this a from these first two terms and write log x in brackets minus log 1 plus bx. And we'll leave the d outside the brackets. So now we've got 1 over x y equals a times, well, by the laws of logarithms, we've got the logarithm of x. Let's leave a bit more space. The logarithm of x divided by 1 plus bx. I seem to have gone back to curly brackets again, but what the hell. Right, let's just 14, we'll call that equation 15, that equation 16, and that equation 17, right? So y is equal to ax times the log of x divided by 1, let's make that look a bit neater, x divided by 1 plus bx plus, whoops, plus dx, right? In fact, you could actually leave the x outside the brackets. So we've got x times a log x over 1 plus bx plus d. Right, there we are, and that is the solution. So I hope that's not been too long-winded and torturous for you, but we finally got there, and that is a solution to the original non-linear equation in equation 1. So once again, if we solve equation 1, we get the equation in equation 18. So I hope that's been okay, and that you will come back and visit more of my videos for more mathematics lessons and further intrigues on ordinary differential equations. So until then, I bid you farewell for now. Goodbye.